So we now have a new set of word problems in Chapter 1, Section 7. These are the sections entitled More Application of Linear Equations with One Variable, meaning these are word problems that you supposedly can solve with just a single variable. Then obviously you move forward into two variable section of the book. You would then solve word problems using two variables. Ironically, I find this first problem, the example that they put in Chapter 1, Section 7, to really be kind of a two variable problem. And so I'll show you how they do it, and then I'll tell you I think it's really a two variable problem. This is not really fair to label this a single variable problem. What they do is they solve this simple part of the second half of the two variable problem and just plug it in. So I'll show you how to do that, but I really earnestly think this is a two variable problem. Now the question works as this. It's a $15,000 to invest. Some of the investment at 8% and some at 7%. Now presumably the person, the most logical thing would be, I'm going to invest everything at 8%. So there must be some increased risk at 8% than at 7%, which is why they're spreading the risk out a little bit. But at the end of the year, their actual earnings was $1,110. So the way this problem works is you have $15,000 to invest, and that's made up of X dollars at 8%. And this is where I think there's a little bit of trickery when it comes to it's only a one variable problem. What they say, the rest that is invested is 15,000 minus X. Now, if it were me, this would be the amount invested at X, and this would be the amount invested at Y. And then Y, you'd have X plus Y equals 15,000. And what you would discover is that you can solve for X using Y in this equation and plug it in. So to me, it's a little bit of trickery, but that's okay. This is really X plus Y equals this, but they're doing X plus 15,000 minus X to total 15,000. And if you work this out, you would find out that 15,000 equals 15,000 because the two X's go away. So that's a little bit of trickery. Now, what we find, though, is the investment return then is equal to this. So we have X times 8%, and we have 15,000 minus X, also known as Y if you're doing two variable solution, minus X times 7%. So now we're going to solve for X. What's interesting about this is that the X terms are going to be very small, less than 1. And normally in an algebraic problem, a lot of times you'd get 2x, 3x, 5x, that kind of thing. In this case, we're going to have 0.08x and 0.07x. Don't let that distract you. It's fine. It's going to work out just fine. So what we're going to do is we're going to multiply all this out. And we get 0.08x plus, and now 15,000 times 7%. I have to look that up real quickly. 15,000 times 7% is 10,500 minus 0.07x. So we're going to combine terms here. We're going to wind up 0.0x minus 0.08x minus 0.07x is 0.01x. You see that? Positive 0.08x minus 0.07x. And then we're going to move this 10.5 to the other side. And that's going to create, that's 1,050. 1,050. So we're going to subtract that from both sides. This will leave us with 60. So you subtract minus 1050 from that, you get 60. Now we're going to divide both sides by 0.01. And this is going to give us X is equal to 6,000. Now, if X is 6,000, so that's $6,000 that was invested at 8%. That means that invested at 7% was another $9,000. $9,000 invested at 7%, because this plus that must total 15,000. So 6,000 plus 9,000 equals 15,000. And this is fairly easy to check. We have $6,000 invested at 8% and $9,000 invested at 7%. And we can multiply that out and add them up. That's $480. That's $630. So 480 plus 630, in fact, does equal $1,110. Now the question, we need to go back and look at the question though. What we're asked is, how much did she invest at each rate? And so the answer is $6,000 at 8% and $9,000 at 7%. So that would be the final answer to this, is that we had $6,000 invested at 8% and $9,000 invested at 7%. And that would be the final answer to this question. Now, you got to be able to do this problem. You have to be able to do this problem because there's going to be one like this on the test. And this is, just letting you know up front, I'm going to put a problem like this on the test. All right, so that's one type problem from this chapter. Another type problem from this chapter is a travel problem. And most algebra students have seen these problems before. Most algebra students don't like them. It's one of those, the train leaves New York at 6 p.m. traveling at 50 miles an hour, and a train leaves Boston heading toward New York traveling at 70 miles an hour. What's the name of the conductor in each train? I mean, it seems like that almost. It seems totally random, but there really is a method to the madness. And we have here as a sample problem, we have a car. We have a car traveling from one city to another. And we have another car traveling in the opposite direction from the city B. So this guy's going from city A to city B. This guy's going from city B towards city A. City is irrelevant, of course. What is relevant is that they leave at the exact same time, and the distance they travel and the speed with which they're traveling. Those things are relevant. So we find out that this car leaving from A going to B is going 55 miles per hour. Find out that this car is going 50 miles per hour. So now the question will be, and you got to check the question here, how long will it take them to meet? How long? So we're asked the question, how long? We're asked the time question. Time. How much time is required? Now, there's one piece of information we still haven't written down, and that is the distance. They are going to travel 157.5 miles is the total distance traveled when added together. Now, they're each going to travel a portion of that, but in total, they're going to travel 157.5 miles. Now, the way this works is distance for a car going from A to B is 55 miles per hour times how long they travel, time. The question we're being asked. And the distance this car travels is 50 miles per hour times time. How much time? That's the distance this car would travel. And these two distances have to equal the total, because this portion of it is this section here, and this portion of the distance is this section here. The total distance traveled, so the distance traveled is the speed by which you travel and how long you drive it. So for instance, I'll give you an example. If I drive 30 miles per hour for 1 hour, I've gone 30 miles distance. If I drive 30 miles per hour for 2 hours, 30 miles per hour for 2 hours, that's 60 miles. In this case, if I go 55 miles per hour for whatever the length of time until the two of them meet, that's the distance I've traveled. And if I go 50 miles per hour for whatever length of time the two travel till they meet, I've gone 50 miles per hour times the time. That gives us the total distance, and the total distance here is 157.5 miles. So now solving for this, we have 55t plus 50t is 157.5. So that's 105t is equal to 157.5. All right, so now we're going to divide both sides by 105. And that is going to work out, divide both sides by 105. And this is going to work out where time is equal to, that looks like about an hour and a half. So 1.5 hours. Careful that you know the actual measurement here. This is miles per hour, how long they're going to travel, and how many hours. This time is solved in hours because they're going 55 miles per hour. So total is 1.5 hours. That's how long it takes until the two cars meet. So this is a very common problem in the algebraic world, is a single variable problem with two travelers either traveling the same direction and one overtakes the other, or traveling from opposite directions towards each other and they meet. And the question is sometimes asked how long. Sometimes it's asked how long in terms of time. Sometimes it's asked in distance. If one driver leaves from city A and is driving 50 miles an hour but leaves an hour earlier, and the next driver leaving from A is going 70 miles an hour, how many miles before driver B catches up with driver A? And that's done the same type way in terms of the way the solution is worked. And so these kinds of problems, objects in motion, and solved with a single variable linear equation. This is how these are done. And so those are two examples from chapter 7, one on finances, one on travel. And so you need to know how to do those two types of problems.